Hey guys.
Hello.
Hey, Moshe.
Alrighty, people coming in. Looking good. Gonna share the screen. Nice. Oh, we even have two Jamies. Very cool. Yeah. How's everybody doing? Chat. Yeah. Yeah, we missed you last week, Michael.
Oh yeah, well, 6 p.m. is past my bedtime.
That's fair. That's fair.
I'm on Greenwich Mean Time.
I was thinking about you because I mentioned something about string theory.
Oh,
Do
you associate me with string theory?
Well, you know. Well, I just figured, well, you know, it got to your point, and we were talking about building things out of harmonic oscillators, and there was like a sort of way of interpreting like a variable number of oscillators as like a string. And
right.
In a way, it made clear that just from the construction that like, you know, this string could like sort of be representing like all sorts of different symmetry groups. And so, you know, suggested that like string theory is like kind of like you're always saying, you know, it's like a sort of a mathematical device, and maybe so, because, you know, as you could see, like, you know, depending on how this thing vibrates, okay, now it like kind of looks like this particle or it looks like that particle. But is that just, maybe that's just like the epicycles, you know, in ancient astronomy, where, yeah, you can simulate any motion in the sky that you want, you know, with adding epicycles upon epicycles, but you're really understanding what's going on. Anyway.
And of course, you can use math to explain anything you want, whether or not it's relevant. You know, to me, and to me, I guess, you know, I make the distinction. Well, I'm an engineer, so I'm more of a practitioner than a theorist. But to me, math is good. But until you have empirical evidence for the math, it's not science. And so things like string theory, quantum theory of gravity, they're interesting mathematical theories, but they're not science until there's empirical evidence. That's my theory. Of course, I've had some very vehement controversy over that. Somebody in the other...
I look at string theory indeed as very similar to mathematics. With math, for instance, with calculus, you can use it to express Newtonian mechanics, or you can use it to express all kinds of other things, but calculus by itself does not make any physical predictions whatsoever. Same thing, that's my view of string theory. In and of itself, it doesn't make any predictions whatsoever, but you can use it to express any of gazillion different physical theories. And apparently it is useful, it is practical for expressing some physical theories. And in this case, then it has some merit analogous to the merit of calculus.
Yeah, or even just all these harmonic oscillators. You know, you can kind of, like we've been seeing, you know, like so many random things in physics can be described in terms of, it's a bunch of, you know, oscillators. You're just treating them in a certain way. Does that really mean that there are actual harmonic oscillators? In some sense, sure, but maybe not in an obvious
Well,
sense.
but it does describe things that have been discovered empirically. And string theory, actually, Moshe, there is a prediction. The major prediction in string theory is a spin-2 boson, a graviton. Again, which is an interesting theory, but gravitons have not been discovered yet. So the whole field of quantum gravity is to date speculation. Although there are physicists who base their entire careers on it, but it's still just theory.
Okay, Michael, let's make a pact. Let's make
Yes.
a pact that we're not going to bring up for the time being, we're not going to bring up the fact that gravitons have not been discovered for at least the next 100 years. If 100 years from now, still no gravitons, then we'll talk about it.
Well, I certainly will not bring it up at the New York quantum theory meetup.
Well, not for
but I
the next
reserve the
100
right
years.
to bring it up elsewhere.
Well, with that, maybe we should get started. I wish Victor was here in a way, because he last time raised the most objections, I think, to the idea of having indistinguishable particles. So I was gonna, begin kind of clarifying, what we mean, or I mean, by an indistinguishable particle. What I mean is indistinguishable with respect to the tensor product. In other words, when we talk about indistinguishable particles in quantum mechanics, what we're talking about is the fact that, in quantum mechanics, systems combine using the tensor product. If you have a bunch of Hilbert spaces, you tensor them together, which is like, a specific mathematical operation that's supposed to represent, physically, what are the allowable states of, these two systems taken jointly. And we know that, basically the power of quantum mechanics comes from the fact that, the way that systems combine is richer and more powerful in a way than classical systems. Because you can have superpositions of different, tensor states, you have, entanglement, and this gives you a lot more room to play with. Now, indistinguishable with respect to the tensor product means that if we permute the subspaces in the tensor product, it comes to the same thing. In other words, the particles are in some sense insensitive to how they're being combined. And in that sense, they're indistinguishable. And, generally speaking, in normal quantum mechanics, leaving aside interesting systems like anyons, which can, appear in two-dimensional systems, maybe we can talk about that later. Basically, the indistinguishable particles come in two types, bosons and fermions, bosons being in the permutation symmetric state and fermions being in the permutation antisymmetric state, which just means that if you permute the particles in the tensor product, the whole thing picks up a negative sign. So I thought, since last time, we discussed basically bosonic quantization, where you take a single particle Hilbert space, you introduce a harmonic oscillator for each basis state, and then there's this sort of nice way of mapping, states of single particle system onto this field and mapping operators on the single particle Hilbert space into operators that act on all of the resulting, permutation symmetric particles at once. And that in some ways, the Fock space, the space of the oscillators is actually, in some ways you can look at it as just a convenient way of parameterizing the states, assuming that the particles are permutation symmetric. In other words, if you look at, given X number of particles, like, what's the number of permutation symmetric basis states? Well, it turns out to be like, exactly the number. So for example, if you have, say you're looking at the subspace of, say, two oscillators where, you're looking at total number 2, how many ways are there to get 2 excitations across 2 oscillators? You can have 2 in the first, none in the second, 1 in each, and 2 in the second, 0 in the first. So there's 3 states. And these correspond to the 3 permutation symmetric basis states of the 2 particles. So the numbering works out. But I felt like there was like a little bit of hesitancy in sort of seeing exactly how this susses out. So I decided it'd be fun today to talk about fermionic quantization as a comparison, see how it's similar and how it's different from the bosonic case. And then we'll discuss the spin statistics theorem, because this came up last time as well, and I thought it would be good to talk about it. It's often said that bosons are, they're permutation symmetric particles or whatever, and that they have integer spin. And fermionic particles, which have to be in the antisymmetric state, have half integer spin. And it's often just said like, oh, that's how it is. But there's actually no, you might say, necessary connection. Because on the one hand, we're talking about what happens to particles under permutations in the tensor product. And then on the other hand, we're talking about the behavior of the particles under rotations. And so, you actually have to prove that there's a connection, that we, given some assumptions, we ought to quantize quantize integer spin particles as bosons in some the relevant physical circumstance, and we ought to quantize half integer spins as fermions. And so those kinds of arguments go under the heading the spin statistics theorem, and it goes back to Pauli in the 30s and stuff. And often involves using a lot of like relativity and fancy stuff. But there's a sort of more elementary argument for it due to Berry and Robbins in the 90s that we'll talk about at the end, where they give a very interesting construction involving the oscillator representation of spin that combines in one operation the act of permutation in the tensor product and the act of rotation. And we'll see that you can get something like the spin statistics theorem. So that's where we're going. That's planned for today. So for bosonic second quantization, as I say, we assign an oscillator to each degree of freedom of some single particle Hilbert space. The number operator of each of those oscillators keeps track of how many particles are in that state. It works out that this Fock space corresponds dimensionally to a tower of permutation symmetric tensor products of 0, 1, 2, 3, etc. particles. The use of the harmonic oscillator just basically imposes this condition that the second quantized particles be permutation symmetric. We have creation and annihilation operators for the different oscillators, and these oscillators are tensored together, and so we sort of tensor the creation and annihilation operators appropriately with identities. So they act on the appropriate subspaces. If we have bosons, we have multiple creation and annihilation operators, they're supposed to follow these commutation relations, where basically, creation annihilation operator on the same oscillator, their commutator is just basically 1 if they're acting on the same oscillator. Okay, so here's the thing. If we want to second quantize fermionically, we have to do a little different, something a little different. First of all, the first big difference is that our oscillators can only have 0 or 1 excitations. At maximum, only 1 fermion can be in a given state. That's basically the Pauli exclusion principle. One sort of way of initially thinking about this is, what we want is the fermions to be in an anti-symmetric state. So, this is like a little map right here that antisymmetrizes 2 states. You have A and B, 2 states, and to take their antisymmetric tensor product, you do A tensor B minus B tensor A. So obviously, if A and B are the same, then that's just going to give you the 0 vector. And so, like, in a way, that's like the idea, right? because the states have to be antisymmetric. They can't, no two fermions can be in the same state. And we're going to be modeling this using the fact that these oscillators can only have 0 or 1 excitations, because remember, each oscillator is associated with one of the basis states of the original single particle Hilbert space. So another consequence is that, if we have bosonic creation and annihilation operators, it doesn't matter the order in which we create the bosons, but it does matter for the fermions. In other words, if we, create a fermion in the jth state, followed by a fermion in the ith state, and we compare that to what happens if we create the fermion in the ith state and then the one in the jth state, we'll see that the state you get is just, multiplied by -1. In other words, the particles are going to be in an antisymmetric state, so if you permute them, it's going to pick up the -1. But also this applies to the, the creation operators as well. Now, that leads to different commutation relations between those creation and annihilation operators. Specifically, instead of using the commutator, as you do in the bosonic case, you're going to use the anti-commutator, which is just basically like the sum of them taken in the two different orders. And so we just sort of swap commutators for anti-commutators. So, what's a concrete, matrix representation of this? The first thing to observe is that it's kind of nice that, the fermion excitations are capped at 1, because we can just basically use 2 by 2 matrices for their creation and annihilation operators. But if you just did that, then you wouldn't get this sign flip here. So we need to add a little extra in order to make sure that the fermionic commutation relations are satisfied. And actually, there's a really neat trick that you can use to make this like...
One moment. Can you go back a little bit to the anti-commutators?
Yeah.
Okay. The first two anti-commutators, I see those very clearly. This comes from the expression that you have on top with the anti-commutator of A and B. The lower anti-commutator, Fi, A plus J. If I is different from J, then it is the same as the other two that you have on top of it. If I is equal to J, then the anti-commutator is equal to 1. This is something that is not obvious to me. Why should the anti-commutator be equal to 1 when I is equal to J?
Are you sort of asking, like if we worked it out?
Yeah. I don't say that it's wrong. It is just not obvious to me.
Yeah. I think that's right.
I think it's right, but let's see.
Let's double check, double check on the old Wikipedia. Did I get it right?
If I is equal to J, then F star is equal to 1.
Then basically what you have there is the number operator. Yeah, if I is equal to J, then you have Fi star.
Right.
Minus a plus Fi star. So you have twice the number operator.
Yeah, I mean, that's okay. Yeah, that's the right answer. But
yeah. Again, I don't argue. I don't say that it's wrong, but I just don't. I'm not sure I know exactly what it means.
Yeah, like what's the why? Why is it like that? I'm trying to think
Yeah,
of an interesting argument.
because offhand, my guess would be that it should be equal to 2 delta ij.
Okay. I mean, yeah. I mean, depending on your convention, sure, that could be the case. That's fine. Yeah, yeah, totally.
But doesn't matter. Let's just go ahead, continue.
It's fine.
I'll think
That's
about that.
your,
Think about like, yeah, what's the right intuition there?
Yeah.
I
But
will.
again, I do not claim that it is wrong, okay? It is not wrong.
Yeah, I understand. Yeah. Um. So okay, well, so how can we get those relations? I mean, maybe by seeing, you know, the sort of concrete construction, it'll become sort of clear a little more. Um, so we have, you know, these 2x2 matrices that are our creation and annihilation operators. Now, suppose we have, you know, 5 oscillators or whatever, and we want to get these commutation relations.
well, if you multiply the two matrices, then it's going to be 1.
Yeah, so we have to add a little extra. So what we're going to do is, so here's, you know, the annihilation operators for, you know, oscillator 0, 1, 2, 3, 4. And what we're going to do is basically impose a kind of ordering, like known as normal ordering. And instead of just tensoring the Fs with identities on the other oscillators, we're going to tensor them with Zs on this side. So for example, suppose we start in the vacuum state and we apply F4. All right, you know, it creates you know, I suppose we're using the creation operator. It creates, you know, a fermion over here. But there's no states in these oscillators. So like these Z's don't matter. But if we, you know, say apply, if there are some excitations in those oscillators, then the Z is going to flip the sign. And so if you construct these matrices, then they will follow the right commutation relations. So for example, we can do it here. This constructs the fermion operators, and then this tests them. So it just looks at the anti-commutators and makes sure that these are 0 and these are, just give the identity if they're equal. And
1 moment, can you tell us again what the Z's are? What is
it's the Pauli Z operator. So, you know, 1, 0, 0, -1, or whatever.
Okay.
So, you know, basically the idea is like, if we applied it like F4, F3, you know, F2, F1, F0, then, you know, since we're sort of creating them in that order, the Z's won't matter because at the time when you're applying each of the operators, there's nothing in those oscillators to get even hit with a negative sign. But if we swap the order and instead do say like, you know, F0, F1, F2, F3, F4, then the Z's are going to come into play. And so that sort of gives us this idea that if we swap the order in which we apply the fermion operators, we get this -1.
Okay.
So anyway, this, you know, this program, you know, outputted true or whatever, so it works. Maybe not the most, I don't know, it's like, look at it. Actually, let's just do, you know, two oscillators, 2 fermions. So, you know, this is what we get. These 2 matrices are the annihilation operators for those for the 2 fermionic oscillators. For 3 and so forth. You know, not that visually interesting. But as I say, this piece of code here checks that the commutators are right. So it takes the commutator of, you know, pairs of them, and, you know, looks to see if this first line's true, and then this looks to see if the second line is true. And it's nice because, you know, when we were playing around with the bosonic stuff, we were sort of, you know, we had to technically allow for, you know, however many excitations you want in these oscillators. And so, you know, we never were getting exactly the right commutation relations, because we're using like a finite dimensional truncation. But here, you know, the space is legitimately finite dimensional. So it's kind of nice. So, all right, so now we know how to construct, you know, creation and annihilation operators with the right commutation relations for, you know, n fermionic oscillators. We want to quantize an n-dimensional single particle Hilbert space fermionically. So just like in the previous case with the bosons, we now have to talk about, you know, what a tower of antisymmetric multi-particle states looks like. You know, before we would just, you know, we would look at, you know, for 1 particle, 2 particle, 3 particle, what are the permutation symmetric states in the tensor product? Now we're going to look at, you know, what are the permutation antisymmetric states with that number of particles. So first, you know, recall that, you know, we can define the parity or like the sign of a permutation as basically -1 raised to the power of the number of transpositions in the permutation. If we want to antisymmetrize a bunch of states, basically what we want to do is, you know, take the states, take their tensor product, you know, given, you know, for each permutation of those states, tensor them together in that order, but also multiply each one by the parity of that particular permutation. So as I say, again, you take, you know, n states, go through all the permutations, multiply, you know, the resulting state by the sign or parity of that permutation and add them up. And that's how you antisymmetrize, you know, a bunch of states. Now, if you want to calculate the basis states for the permutation antisymmetric subspace of n particles, who each live in a d-dimensional Hilbert space, what you do is you basically take the, you know, d basis vectors and form sets of them that have like n elements and like no repeats, and then antisymmetrize them. And you'll end up with, you know, d choose n basis vectors. And, you know, you can, you know, kind of collect those together into like a rectangular matrix that will, you know, translate between a vector whose dimensions are like, you know, this, like the number of antisymmetric states, and it translates to a state of the antisymmetric states. So specifically, this code here, you know, just gives you the parity or sign of a given permutation. This code right here antisymmetrizes a list of states. You see it goes through each permutation, tensors them together in that order, multiplies that by the parity, sums it all up. And then this basically generates the this linear map formed from the antisymmetric basis states. So it calculates those by, you know, basically going through, you know, all the different sort of combinations of the basis states of the original system, antisymmetrizing them, you know, ignoring them if they're just like 0 or whatever, which is going to happen when, you know, 2 of the states are the same. So for example, so, okay, so here's the example, right? So suppose we have 2 spin half states like this. First, let's look at what happens when we anti-symmetrize them. So I started out with this spin half state and this spin half state. And then this is their antisymmetric product. And we see that it's, you know, basically looks like a singlet. we can check that it really is antisymmetric by swapping it, which you see here. And you see that under a permutation, this whole thing remains the same, except it gets multiplied by -1. We can then look at here, this function here, as I say, gives you this transformation built out of the antisymmetric basis vectors. So, you know, suppose we have, this is saying, suppose we have two particles, each of which live in a two-dimensional Hilbert space. In that case, there's only one state that they can be in that's antisymmetric. And that's, you know, the famous singlet state itself right here. But for example, you know, suppose we had three-dimensional particles. You know, it turns out that there are three antisymmetric states of two particles, each of 3 dimensions. And they are here, the rows of this matrix. Because it's 3-dimensional, if we take some 3-dimensional state and, you know, basically multiply it by the adjoint of this, we're gonna get a state, you know, that's, you know, 3 by 3 dimensions. Or conversely, you know, if you have a state, an antisymmetric state of, you know, 2 3-dimensional particles, you can multiply it by this transformation that just gives you the 3 components. And so you can, like, you know, look at this, like suppose we had, you know, 3 particles, each of 3 dimensions. It turns out there's just one antisymmetric state. Okay, et cetera, et cetera. You know, what if it was 4 and we had, you know, 2 particles? Then, you know, we can see that we have 6 antisymmetric states of 2 particles, each of 4 dimensions, and so forth. Now then basically we're gonna put these 2 facts together. So, you know, for example, suppose we start with 3, you know, an original single particle Hilbert space of 3 dimensions. And so we introduce 3 fermionic oscillators. We construct the total number operator. We then construct a permutation matrix that rearranges the number operator so that its eigenvalues are in order along the diagonal. We brought this up last time in the permutation symmetric context. And the point of doing this is, you know, we're going to rearrange the Fock space so that in this case of 3 fermionic oscillators, we can decompose the state as a kind of concatenation of a 1-dimensional Hilbert space, a 3-dimensional Hilbert space, a 3-dimensional Hilbert space, and a 1-dimensional Hilbert space. Why? Well, look, so we have 3, the original dimensions of the Hilbert space, the single particle Hilbert space is 3. So we look, what's the antisymmetric states for just one of those? There are, sorry, I should say, okay. So the first one here is just the vacuum state. So that's just the state with no particles. If we just have, and so it's obviously 1-dimensional. If we then have 1 particle, we just have 3 basis states, which correspond to the 3 states of the original single particle Hilbert space. And that gives us our first H3 here. If we have 2 particles, then we see that, again, the dimensionality is like there's 3. There's 3 antisymmetric states of 2 particles, and that gives us our H3 there. And then suppose we have 3 particles, then we see that there's just 1 antisymmetric state. And so we see that there's this correspondence between the basis states of our oscillators and the number of you know, permutation antisymmetric states. So we can kind of lift this, which is like the oscillator states of the oscillators, into this, which is like a tower of, okay, here's like the vacuum state, Here's the state of, you know, one particle. Here's the state of two particles, anti-symmetrized. Here's the state of three particles, anti-symmetrized, etc. So, you know, here's the code. Basically, this constructs the permutation that we want to kind of like rearrange the basis, because again, you know, it's like when you naively just tensor the oscillators together, the you know, the order of them, or like the labeling of the basis states, has to do with like the order you get from the tensor product. But we want to kind of rearrange things. So, you know, for example, if we just build our fermionic operators and then create the overall number operator, we look at it, it looks like this. So we can see already the dimensionality works out, because we have 1, 0 state. We have 1, 2, 3, 1 states. We have 1, 2, 3, 2 states. And we have 1, 3 state. And that corresponds exactly to what we wanted, 1, 3, 3, 1. But, you know, you notice that the 1s and the 2s and the 3s are in this like kind of order that is the result of just naively tensoring them together. So what this permutation matrix does is it just rearranges this matrix so that you just have 0 and then the 3 1s, the 3 2s, and the 3. Okay? And the point of just representing as a matrix is then like we can, you know, transform the number operator by wedging it in between the permutation matrix and its adjoint. But then we can, of course, also take a state and permute the state too with the same operator. So for example, what we can do is, given just like some random state in the Hilbert space of the oscillators, we can rearrange it using the permutation operator, and then we can split it into these pieces. In other words, we'll split it into a 1-dimensional piece, a 3-dimensional piece, a 3-dimensional piece, and a 1-dimensional piece. And so we do this. So we extract these like sort of sectors. This 1-dimensional state, that's the vacuum, 3-dimensional, 3-dimensional, and 1-dimensional. So then, you know, for each of those, we can, you know, use this function up here to get the this transformation from, you know, like this guy, for example, we can use the above transformation to send this into a state of, into the states of 2 anti-symmetrized particles, each with an original Hilbert space of 3 dimensions. You know, concretely, again, you know, it was, you know, in this case, be okay, 2 particles, each of 3 dimensions. We see that it's a 3-dimensional Hilbert space. And so we can basically use this guy, or specifically its adjoint, you know, columns and rows flipped, to transform this state here into this state, okay? So these contain the same information, this guy here and this guy here. So this is 3-dimensional state, and this is a state in the tensor product of 2 of the particles. And because we're only allowed to be in one of these 3 states, each of those states corresponds to an antisymmetric state. This is itself antisymmetric. And we can get all the antisymmetric states in that way. Furthermore, for the, you know, the case of 3 particles, remember, if we do, okay, 3 particles, each of dimension 3, we just had 1 antisymmetric state. And so, you know, that corresponds, basically, you take this, you multiply it by that 1 state, and you get this. So there you go, here it is. You take, this is it, that's basically the whole story. You know, it's like, this is how you quantize things fermionically. It's like, you know, you have some d-dimensional single particle Hilbert space, you introduce d fermionic oscillators that have these commutation relations. You know, basically you're doing something to the effect of, you know, sort of rearranging the components of that, of the state vector in that oscillator space and upgrading it so that the components actually refer to these basis states in the antisymmetric states of 0, 1, 2, 3, and 4 particles. And so you could like do it all at once, like, you know what I mean? Like you could sort of like, you know, you could use these transformations that take, you know, these components to these vectors and, you know, like upgrade the fermionic, like creation and annihilation operators like themselves or whatever, so that like you wouldn't have to necessarily do this by hand. But of course it's useful to just stick with this, right? Because this is like a lot of dimensions, you know what I mean? But you don't need to, you know, keep track of any more information than what's in this. Because remember, it's like for two particles in this case, there's only 3 states. So you really only need to keep track of like these 3 complex numbers. Now, if you really wanted to be, you know, whatever about it, you could be like, oh, well, those 3 numbers refer to specifically like one of these states. That's like in the tensor product of 2 particles. And so, you know, you could just, you know, work completely with this state and kind of upgrade your creation and annihilation operators so that they, you know, act on these kinds of states. But, you know, what's the point? Because you could just, you know, work over here. It's the same information. So, so that's really it. That's fermionic quantization. Just like in the bosonic case, we're using the harmonic oscillators more or less because they provide a very useful parameterization since the number of states of a given total number of the oscillators corresponds to, in the bosonic case, the number of permutation symmetric basis states of however many particles, and in the, you know, fermionic case, the number of antisymmetric basis states. So any questions about that? Yeah, like, you know, let me know if anything occurs to you. You know, bosonic quantization, fermionic quantization, really no harder, you know, one's no harder than the other. And in fact, fermionic might be a little bit easier because as I'm saying, you know, the number of excitations in each oscillator is capped at 1. So, so that brings us to our next topic, which is, you know, what is the connection between spin and statistics? So like I was alluding to before, you know, bosons are supposed to be permutation symmetric particles. Fermions are supposed to be permutation antisymmetric particles. Fine. But then we all know that there's also, you know, supposedly this connection to the spin of the particle. In other words, the bosons, oh shit, this is like the bosons are supposed to have half integer spin, and the fermions are supposed to be, sorry, what did I say? Permutation symmetric, integer spin, fermions half integer spin. And, you know, nothing we've said so far implies that this should be true. Okay, like you actually need some other, you gotta do some other stuff to actually get that far. You know, this came up last time. We were talking about different ways to rotate things, and it was asked, you know, what, you know, effectively, you know, you can rotate, you know, a point in 3D by acting with, say, an SO3 matrix. Or you can represent a point in 3D with like a spinner and rotate it with the SU2 matrix. And the question was sort of like, what's the difference? And, you know, the idea is that you actually get a little bit more when you do a rotation with SU2. Recall that in addition to keeping track of the direction that something's pointed in, a spinner also has a phase. And specifically, you know, the direction it picks out is like invariant if you rotate the overall phase. And we know that, you know, when we think about polynomials, like this is no different than if you like take a polynomial or like a monomial that has like one root and you multiply it by any complex number, it doesn't change the root. And so, you know, what it all sort of susses out to is that SU2 is the double cover of the normal rotation group. And so for each element of the normal rotation group, there's 2 elements in SU2. And so you get this thing, you know, that people talk about. Basically, if you take a spin half state and you rotate it, you know, using some exponential Pauli matrix, 360 degrees, the state gets multiplied by -1. And then if you rotate it another 360 degrees, the state comes back to itself. So for, you know, spin half states, it takes 2 full turns for them to come back exactly to themselves. And
Can I ask you something?
yeah,
Let's say you have a spin 3 halves. Does it rotate 3 half rotations or 1 half rotation?
more like
the net effect is 1 half, but in actuality, or let's say a graviton, does that rotate twice around for every?
Yeah. So basically, what happens is that the half integer states, you know, you rotate them 360, they go to the negative themselves. And for bosons, or sorry, I shouldn't use that term yet. For integer spins, that doesn't happen. But for the higher spin states, like you're saying, for like 3 halves, for 2, you know, that happens, but the phase winds around more times on its way there.
Right.
So so here's a nice little visualization of this. So this is going to be, at first, we'll look at for a spin half particle. So what you see here is a spin half particle, and its original location is given by this yellow dot. And it's rotating around the z-axis, and its current spin axis is given by light. Meanwhile, the original phase is given by this yellow arrow, and the current phase is given by this white arrow up here. So, okay, so we'll start the clock when the white guy hits okay, the clock has started. We're rotating, and then we've made a full rotation. Look, the phase is the negative of itself. Okay, we're doing another rotation. Okay, after 2 full rotations, oh, the phase is back to where it began. Okay? Does that make sense? If we then look at a spin 1 state, we'll do the similar thing. Now there's 2 stars. Okay, we're doing it. We're about to make a full rotation. And look, the phase is like exactly the same as when it started. We're doing it again. Okay, every time we make a full rotation, the phase just comes back to itself. No funny business. But then we can look at, you know, spin 3 halves. Keep on trucking, you know. And we're doing it, and boom, that was 1 full rotation. The spin was the negative of itself. And then we're coming in, boom, 2 full rotations, it came back to itself. Again, it's rotating, and then, oh, 1 full rotation, it was the negative. Going again, and 2 full rotations, we're back to where we started. We can look at spin 2. Spinning around. Boom, that was 1 full rotation. Phase was back where it was when it started. And blip, blip, blip. Okay. So yeah, so, you know, you see that, you know, depending on, you know, it sort of depends on the constellation, exactly the behavior of the phase, you know, in between these rotations. But you can see that it's true, you know, under rotation for a half integer spin, a full rotation thing picks up a negative sign. And then after 720 degrees or 2 full turns, comes back to itself. For integer spins, this is not true. And they come back to themselves after just 1 rotation. So there you go. Now you get that. Okay, so like, it might make sense, you know, that half integer particles, half integer spin might have something to do with fermions, because, you know, both involve a -1, right? You know, it's like you rotate a particle 360, a spin half 360, you get this like -1. For fermions, if you permute them in the tensor product, oh, you get a -1. So you're like, maybe, you know, maybe they have something to do with each other. But I mean, that like assumes something really big, which is like there's a relationship between rotations and permutations in the tensor product. You see, in the one case, we're talking about, say, like fermions per se, we're thinking, you know, you tensor these guys together, whatever, and then you swap them in the tensor product and it picks up a -1. The other case, we're talking about like turning something 360 and then it gets multiplied by -1. And so essentially, you know, the spin statistics theorem posits that there's a connection between these things, all right? I emphasize this because, again, there's no mathematical obstruction to quantizing, say, half integer spins as bosons. In fact, we've done it. That's the, you know, that's like the oscillator representation of spin. You just take a bunch of spin half states, quantize them as bosons, and you get all the spin J states. You know, you can, certainly there's permutation symmetric states of spin half states, you know what I mean? You know, for example, you know, up, down, plus down, up. There you go, there's one right there. If you permute them, there's no factor of -1. If you rotate one of the guys a full turn or whatever, I mean, that breaks the permutation symmetry. If you rotate them both a full turn, you know, maybe you get this -1. But essentially, what we have to do is show that there is a connection between rotations and permutations in the tensor product. And that's like essentially what the spin statistics theorem gets into. So again, there's like, you know, there's nothing, you know, just in the definition of a spin half or a spin, an integer spin or a half integer spin particle that necessarily implies that the one is a fermion and the other one's a boson. Like, you actually need to do like a little more work than that. And the usual proofs, which, as I say, you know, go back to Pauli and others, you know, involve some pretty high-powered stuff. Quantum field theory, special relativity, kind of has to do with the dimensions of the space. You know, you may know that like in 2-dimensional systems, you can often have, you can have anyons, which are sort of like, you know, in between being bosons and fermions, in the sense that when you permute them, they pick up like just a phase factor, you know, instead of just being like -1, it's like, you know, just some other random complex number, just another random phase. You know, maybe it gets multiplied by I or something when you permute them instead of -1. And that can happen in 2 dimensions or whatever. But, you know, it gets a little, and maybe we'll talk about anyons because they're cool later on. But for now, you know, we're going to look at this very interesting construction due to Berry and Robbins from the 90s, where they try to give a sort of argument for the spin statistics relationship that doesn't really have anything on the surface to do with relativity theory. And it's especially cool because it involves the oscillator representation of spin in a deep way. And actually, we'll see, and, you know, I mentioned this for Moshe, who's, you know, always wanted me to talk more about loop quantum gravity. You know, this actually, you know, becomes, many of the mathematical elements become key, you know, things that are used in the loop community. So, so let's take a loop at that. So, you know, first, a kind of a bullshit argument in a way, right? like, you know, what's the relationship? Because basically there's three notions that we need to make talk to each other. On the one hand, we have this idea of like a permutation in the tensor product, right? Like that has to do with like how things are tensored together, how things were combined together into like the Hilbert space, right? On the other hand, we have the idea of rotations, and spins transform in these ways depending on their J value under rotations. And then, you know, we have the actual notion of like taking two particles like in space and switching their locations, okay? Those are three separate concepts. And our goal is to show that there is a relationship between them, okay? So then I'll begin with a sort of bullshit argument, right? It's like you take two particles, there's like side by side, and you swap them like this, you know, like imagine you were A, right? What would you see? Like at first you're seeing like, say, my pinky, right? And then like I move this guy over here, and now like this guy is like, you know, this face that's facing him is like, you know, my palm over here. And then we rotate over here, it's like now the thumb is facing him, right? So under like a permutation in space, it looks from this guy's perspective like a 90-degree rotation has taken place. Or sorry, a 180-degree rotation has taken place. Rotation of pi radians. So, okay, so we're thinking, all right, so there might be, so, you know, is there a way of combining then? So that's sort of like an argument, like a spatial argument, which you might wonder, like, okay, so like, is there a mathematical way of saying, well, if combining a swap in the tensor product with a 180-degree rotation? Okay. So we are going to do this. This is what we're going to do. Okay, so first a little review from last time about the oscillator representation of spin, which we're gonna employ here. So, you know, again, what this means is we're going to treat a spin as the second quantization of a spin half particle. So a spin half guy, and it's a bosonic second quantization. So, you know, the spin half is two basis states, say, up and down. And so we're going to introduce two harmonic oscillators to keep track of, you know, the number of guys in those states respectively. And, you know, you can kind of think of this like taking the square root of a spin, like taking a spin, like splitting it into like two pieces. And this notion becomes really useful here. So recall, so like suppose we have two spins. Each one is associated with a pair of oscillators. So we have 4 oscillators in total. So, you know, we have spin A and spin B, and we have an up oscillator and a down oscillator for both, for A and for B. Now, before we talked about, you know, how you can upgrade or second quantize, you know, operators that act on the single particle Hilbert space to operators that act on the Fock space. So the idea, you know, essentially was to like wedge a 2x2 operator in between, you know, basically a bra and a ket full of not numbers, but full of creation and annihilation operators. In other words, here is like a little row vector full of the creation operators for the first spin. Here is a column vector of the annihilation operators for the first spin. Here's, you know, Pauli X. You know, do this matrix multiplication or whatever, and you get this. So, you know, this operator, you know, basically, you know, creation, you know, create, you know, this would be like annihilate a quantum in the down oscillator and then create a quantum in the upper oscillator at the same time that you annihilate one in the upper oscillator and create one in the down oscillator or whatever. Everyone like interpret it that way. But this you know, has all the properties of Pauli X. And, you know, if we take its expectation value or whatever, like we will get the expectation value of the spin, like in the X direction. If we exponentiate this, like e to the negative I times this guy, it will rotate, you know, this spin or whatever around the x-axis. So, you know, this is the way of sort of second quantizing operators. We can take operators that act on the spin half, single particle Hilbert space, that's the standard 2x2 Pauli's, and we turn them into operators that act on like the whole Fock space. And, you know, supposing that we have like a superposition of different J values for these spins, like this will, you know, these will like rotate them all, you know, kind of simultaneously. So we can obviously do the same thing for the second spin. So we have two oscillators for spin B, and so we can get X, Y, and Z operators that act on spin B. So again, so this is like the sort of the basic notion of the oscillator representation of spin. For each spin, we introduce two oscillators, and then we can represent, you know, basically the, you know, generators of S2, X, Y, and Z in terms of linear combinations of the creation and annihilation operators. Okay, so that's all well and good. But you might just, even if you weren't trying to, you know, prove like spin statistics theorem or whatever, you know, you might be like, hey, you know, I got 4 oscillators total here, right? Like what's stopping me from like building spins out of, you know, an oscillator from spin A and an oscillator from spin B? In other words, we could also consider a different way of breaking the system down and consider spins built out of cross oscillators. For example, we could build a spin that's made out of the 2 up oscillators, the up oscillator for A and the up oscillator for B. In other words, here we have, you know, creates an up excitation in A, creates an up excitation in B. And so we get, you know, another set of XYZ operators that are built out of, you know, in a sense, the square roots of the 2 original spins we started with.
Matt, can I ask something? Maybe I missed something, but why are we assuming that A and B are oscillators rather than just vectors? Or are we just assuming that for, you know, mathematical reasons?
So,
I may have missed something.
Well, so, you know, last time we talked about, you know, this oscillator representation of spin, where we showed that you can basically represent a theory where your spin is allowed to have a variable J value. Like normally when you work in the JM representation, it's like a spin half or a spin 1 or spin 3 halves or whatever. You might wonder as a way of thinking about, could we have like a superposition of different J values? And we showed that that's equal to this oscillator formulation of spin. And what you do is you associate a bosonic oscillator with the 2 basis states of a spin half particle. And then you can interpret the higher spin states as being permutation symmetric products of the original spin half Hilbert space. So that, you know, the spin 1, you know, there's 3 components to spin 1. And there are also 3 permutation symmetric states of 2 spin half particles, specifically up, 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 down, plus down, up, and down, down. And so there's this correspondence between those 2 things.
Well, why are we assuming that they're oscillators rather than just a vector, any kind of vectorial entity?
Well, that's sort of the idea, right? So like, you know, normally these operators act on just spinners, you know, like 2-dimensional guys or whatever. And, you know, the idea is to second quantize. What we do is we upgrade each of the we associate to each basis state of the original system an oscillator of its own that keeps track of like the number of particles in that. So, you know, for example, like in this, so you can think about it like these linear combinations here, they act like X operators, Y operators, Z operators on a state that's potentially a superposition of different spin J's, if that makes sense. Another way of saying it is like for example, you know, if you look at the total number operator of the excitations in the, say, up oscillator and the down oscillator, that gives you the J value of the spin that's like encoded in the oscillators. So this is, it's like a different way of thinking about spin. Instead of thinking about, so, you know, it's like you sort of you take a spin and you split it into two oscillators. That's basically the idea. And like I'm saying, you can also view that as like a theory of a variable number of permutation symmetric spin halves, or you can look at it as a superposition over different J values. Or you can just look at it like, here's a spin, and I'm in some sense taking its square root. I'm splitting it into two pieces, and it turns out the square root of a spin is like a harmonic oscillator.
What was this Pauli's approach? I know we're going to get the spin statistics theorem.
No, this is
This is not his approach.
So, you know, this often goes by the name of the oscillator formulation of spin, or the Schwinger. It's often associated with Julius Schwinger. In the context of spin statistics, using this formalism goes back to the 90s and this famous paper by Berry and Robbins, which is a very interesting paper. This one here. Very great paper. Indistinguishability for quantum particles, spin statistics, and geometric phase. So, you know, I highly recommend reading this for more information. And I'm basically going to give a summary of the main points of it. So we have two spins.
I'm sorry, indistinguishability for, what's the name of it? Quantum particle. And this is based on Schwinger's work?
Yeah. Yeah, as it says right here. So, you know, they use 4 harmonic oscillators in which the two spins are made according to Schwinger's scheme, and using those 4 oscillators, they're able to unify permutations in the tensor product with rotations. And so that's what we're going to see right now. So, you know, if there's anything to be said for using the oscillator representation, it's going to come out here in this example. So, okay, so again, we have 2 spins, A and B, and we have 4 total oscillators, 2 associated with A, 2 associated with B, and can interpret them like, you know, each oscillator is an oscillator that's keeping track of the number of up and down quanta. But we could also consider spins kind of constructed out of oscillators like across the 2 original spins. In other words, we could gather together the, you know, up oscillator for A and the up oscillator for B and get X, Y, Z operators built out of those. Or we could take the 2 down oscillators for A and B and build X, Y, Z operators out of those. Okay? Now, suppose we do this and we take, say, like, choose like the Y axis. And we evolve under this, with this guy here. E of negative I theta, rotation of the 1 cross spin around the Y axis, and a simultaneous rotation around the Y axis of the 2nd cross spin. In other words, perform a simultaneous y rotation of theta degrees to the two cross spins. The first built out of the up oscillators across A and B, and the second built out of the cross oscillators of the down cross oscillators. So, you know, what's cool is like, okay, so if you like look at what happens to the original spins during this y rotation, after a turn of 180 degrees or a turn of pi, the two original spins will have swapped places in the tensor product. They'll have permuted themselves. And after a turn of 2 pi, they will return to where they began. Moreover, if we consider doing this with states of different j values, we find that in addition, if we start with half integer states, the overall states multiply by a -1 after a swap. But for integer spins, that doesn't happen. In other words, we have something that looks very like the spin statistics relationship. If we do a 180-degree turn, we get, on the one hand, a permutation, a swap in the tensor product, and we get a -1, specifically when the particles being swapped are fermions, and just a 1 when the particles being swapped are bosons. So let's look at it, okay? So here's some code. You know, this is a little thing that just kind of gives you the phase. So we're gonna, you know, be able to see if the phase is flipped or not. Here's a function that takes a list, an operator, a 2x2 operator, say, and a list of annihilation operators, and it second quantizes them. That essentially does this, wedges the operator between these vectors formed of creation and annihilation operators. We can also second quantize a state by just, you know, multiplying each component of a state vector, two-dimensional state vector, by, say, like creation operator. We can second quantize a spin state. You know, we talked about this before, but essentially this is like, you know, it's like the Majorana polynomial, but like the homogeneous version where there's two variables, and the two variables here correspond to the two harmonic oscillators. Okay. If you have questions about that, you know, we can review that, but not that important for what we're doing here. So what we do is here we create the two oscillators, the two sets of oscillators for spin A and B. We check out our XYZ operators like the normal kind. These are just Pauli matrices. We second quantize those with the A oscillators. That gives us our normal XYZ operators on spin A. We second quantize, you know, each of those operators with the B creation, you know, whatever. And we get the XYZ operators that act on the B spin. And then we do the same for the cross oscillators. So you see, we go through XYZ, and for our annihilation operators, we use the first one of A and the first one of B, and the second one of A and the second one of B for the other guy. We can then look at, say, the total number of excitations in A, which is basically going to give you like the J value of the A spin. This is basically going to be the J value of the B spin. This is going to be the J value of the first cross spin and the J value of the second cross spin. To start off, what we're going to do is we're going to choose two random spin half states, and we're going to load them into our oscillators, right? So, you know, to recall, what you do is you take the vacuum state of the oscillator and you form creation operators that sort of create these single particle states. So this one, you know, again, A state is just a two-dimensional vector. These are the creation say like the annihilation operators that act on, you know, the A spin. There's two of them. And so you basically, you know, multiply the components by the corresponding creation operator, and that gives you the sort of a creation operator that raises the spin half state out of the vacuum. So we sort of load in, this chosen spin half state and the other chosen spin half state into the oscillator associated with A and B. Okay. Then we visualize stuff. So let's look at it. So, okay, we have on the left spin A and on the right spin B. Spin A is in blue and spin B is in red. We can see the original states that we started out with on both the blue and the red sphere as these like dark points, like this blue guy and this red guy. So, this is where blue started out at the beginning and this is where red started out at the beginning. And we are doing this Y rotation. That's a Y rotation of the cross spinners. And, I'm not sure if it's entirely clear, but you can see that this expected rotation axis of the blue guy is oscillating back and forth between pointing where the red guy was and pointing where the blue guy originally was. So continually rotating the cross spins, both around the y-axis, has the effect of a permutation. Moreover, it's like, okay, so here we're at, you start the, actually, let me make it a little bit clearer. So let's just do a pi rotation. Okay, so a single pi rotation took the blue guy to the red guy, and it took the red guy to the blue guy, okay? So this rotation has like swapped the particles, but look at what's happened to the phase. The phase was originally this yellow guy, but now the phase is this white guy. In other words, by a kind of pi rotation that swaps two particles, we pick up a -1, which is what we'd sort of expect from the spin statistics theorem. These are two spin half states. We exchange them and we pick up a -1. If we do the same thing with a spin 1 particle, we do a pi rotation, we see that the blue guy has swapped places with the red guy swapped places with the blue guy, but look, behold, the phase is the same as when we started out with. In other words, under these cross rotations, the basically half integer spins act like fermions in the sense that if you permute them, they pick up a negative sign. And integer spins act like bosons in the sense that if you permute them, they don't. So there you go. Now, one thing that's kind of interesting to think about is like, let's go back to the spin half case here. So if you look at, like actually, and let's just have it just continuously kind of like rotating. All right, so this guy is going to be, bouncing back and forth between red, that's going back over to blue. Okay, so it's like this continual rotation is continually permuting these two particles, and every time they're swapped, we pick up a negative sign we can see here. Now, like, let's look at what the cross spins are doing. In other words, these are the two cross spins. Like, this is the one built out of the two up oscillators, and this is the one built out of the two down oscillators. And it's a little hard to see, I suppose, because it's so tiny. But indeed, you can see that like the expected rotation axis of this guy is indeed just rotating around the y-axis, right? Y, is up and down here. And if we go down here, we'll see that this guy too is just rotating around the y-axis. And in fact, it looks like these guys are always sort of pointed in the opposite direction. Now, one thing that's kind of interesting is the radius of these spheres I've had pegged to the J value of the spin. So we start off with two spin halves, and so the radius of this, of the blue and the red spheres, is a half. But you notice that, like, if we look at what's going on in the two cross spins, the J value is like not a half, okay? In fact, in a kind of limiting case, suppose that we started out with like exactly two particles in the same state. You can see that, this guy is like real small and this guy is real big. Okay. So, this is kind of crucial here. Okay, because basically the idea is this. You can think about, like, okay. For this to work, the oscillator construction is necessary in the sense that you can't represent this so-called exchange rotation simply on the Hilbert space naively of a spin half particle tensored with a spin half particle. And you can see that because when you build the cross spins, this guy has a higher J value than spin half. This has a lower J value than spin half. In other words, this rotation actually rotates you out of the original Hilbert space. And, you need those higher states, like you need a representation that can take into account different J values simultaneously, because you're basically like rotating out of the original Hilbert space and then like coming back into it. And so you sort of take this detour into, the extra space provided by, the two oscillators. And you can sort of think about this as being like the space in which like parallel transport takes place between the one spin and the other. That's sort of how they look at it. Yeah, so I just want to make that point. You need the oscillators. Like you can't construct one of these rotations if you just stick with like the normal Hilbert space. So, all right, is there anything else I wanted to say about that? I guess that was the main thing. Any questions, I guess? So, okay, I mean, you know, to summarize basically what we've done today, we treated the case first of fermionic quantization. It's kind of like bosonic quantization. There is a correspondence between the components appropriately rearranged of, you know, n quantum harmonic oscillators. And in the bosonic case, these correspond to the states of, you know, a bunch of permutation symmetric tensor products of 0, 1, 2, 3, 4 particles. And in the case of the oscillator representation of spin, we can additionally associate each one of those permutation symmetric, you know, states with a spin J state. In other words, we can associate, you know, the spin 0 state with, like, you know, the vacuum state of the two oscillators. We can associate the spin 1 spin half state with the state of, like, total 1 excitations across the two oscillators. We can associate the spin 1 state with the 3 states formed of, like, total number 2 excitations across the oscillators. In other words, 2, 0, 1, 1, 0, 2, and so on and so forth. And so, you know, that's the essence basically of bosonic quantization. Second quantization, on the one hand, you have these components of the, you know, your oscillators. On the other hand, you have the components of, like, a tower of permutation symmetric states. And additionally, say in the case of two oscillators, you can interpret this as a model for spin. In the case of fermions, you know, we have to make some changes. We can have only 1 excitation per oscillator, and the commutation relations are different. And so we saw how to construct the right creation and annihilation operators. We saw how to antisymmetrize states and form, you know, the basis of states for the antisymmetric subspace of n, you know, particles or whatever. And so we saw how to create a correspondence between the components of the fermionic oscillators and the basis states of 0, 1, 2, 3, 4 antisymmetrized particles, where, you know, you're beginning from some original Hilbert space of d dimensions, and d is also the number of oscillators. Then we were like, all right, we've been talking a lot about fermions and bosons or whatever. What is the connection between integer spin and half integer spin? How spins transform under rotations, the fermions picking up a negative sign under full rotation, and this idea of, you know, the half integer spins being fermions and the integer spins being bosons. And, you know, we sort of realized that, you know, in a sense, we're playing around with, like, 3 separate concepts. 1, rotations; 2, permutations of the tensor product; and 3, like, actual exchanges of position. And we saw that Berry and Robbins kind of give us a way of unifying, at the very least, rotations and permutations of the tensor product. So that if we take 2 spins, we can form 2 cross spins built out of oscillators across the 2 and consider rotations of those guys. And if we look at the behavior of the original spins under those rotations, we find that under, like, a 90-degree turn of the 2 cross spins, we get a permutation of the original spins. And if the original spins were spin half, then we pick up a negative sign. And for integer spins, we don't. And so that sort of is at least a suggestive argument that something like the spin statistics relationship is true. Although, of course, you know, depending on the circumstance, you may want to quantize spin half states as bosons, as is premised by the very idea of the oscillator representation of spin, where you can interpret that as a bosonic quantization of a spin half particle. So you can see these things are kind of related. Now, there's another part of this story, I have to say, because this very nice Barry Robbins construction unifies rotations and permutations in the tensor product, but in a sense, we've left the actual positions of the particles somewhat to the side. We want to kind of also take this third idea of like actually swapping the locations of the particles. And so it's like, how does that work? And furthermore, is there a way of doing something analogous to what we've done here, but where we don't just consider a swap of two particles, but in general, a permutation, some arbitrary permutation of the particles? And you can do this stuff basically, and maybe next time I'll be able to talk about it more. There's some aspects of it that I'm still sort of trying to understand, but there's a very cool construction that they use, especially thanks to the help of Michael Attia. So I can briefly summarize what that is, unless there's questions, concerns.
I have a question. This is a little off track, but I'm trying to relate this to the no cloning theorem. And again, pardon my ignorance, but does that only apply to fermions, or does it also apply to bosons?
Yeah, the no cloning theorem applies to fermions and bosons.
So how do we reconcile this if we can, exchange states, or if two bosons can be in the same state, but no cloning theorem says that you can't copy a state?
Right. So no cloning says not that you can't have indistinguishable particles, say. No cloning says basically if you have like a state or something, there's no like quantum operator that takes that state to like two copies of that state. In other words, like if I have, like classically, like if I have, a bit 0 or 1, I can copy it, just, okay, make 2 of them. Now there's like, it's like 1, 1, or it's like 0, 0. In the case of a quantum bit, like a qubit, you have that state. You might wonder, can I just copy it? Can I just get like, now I have 2 of them or whatever? And you can't. And so, that has nothing in particular to do with bosons or fermions. It says you can't clone an unknown state.
2 bosons can be in the same state. Is that correct?
No, with no cloning, it's different. No cloning has to do with the uncertainty principle. If you could make copies of a particle, of a state, you can make, let's say, a dozen copies of one single state. So on one copy, you measure the position. On another one, you measure the momentum. On another one, you measure spin in the x direction. In the other one, spin in the z direction, and so on and so forth. You will be violating the uncertainty principle left and right.
Yeah, that's a really good.
So what?
So
maybe you can violate it. Why not? But I'm trying to reconcile. I'm trying to reconcile the no cloning theorem with the fact that 2 bosons can be in the same state.
But again,
it has nothing to do with bosons. There is a contradiction between cloning and the uncertainty principle. The uncertainty principle implies that you cannot clone the state of a particle. Now, you can say that you don't like the uncertainty principle and get rid of it. You get rid of the uncertainty principle, you can make as many copies as you want.
But then, but isn't that in conflict with the spin statistics theorem that says that you can have multiple bosons in the same state?
No, you can have many bosons in the same state. That's true.
Yeah.
But you cannot make a copy of a state. You can have several bosons in the same state, and you can measure the spin of one boson. Okay, it is one boson. You can measure the spin of another boson, but it's another boson. It's not the same one.
Yeah, and remember, like
It's
when
just not the same one anymore.
when we're talking about the bosons and stuff, you know, recall it's like in the oscillator way of thinking about it, right? It's like you have the basis states of like the original single particle Hilbert space, and then the oscillators keep track of like the number, right? The number of particles in that state. But if you like look at, you know, the actual underlying states of, you know, 1, 2, 3, 4 particles, you know, what that amounts to is these permutation symmetric tensor products. In other words, you know, don't confuse being able to have like two states that are the same with the idea of like, you know, two particles being indistinguishable, because when you permute them in the tensor product, you can't tell the difference.
But not only are they indistinguishable, they could be in the same location.
Sure.
So, okay, but I guess what Moshe said, you can't copy them. They can be in the same state, but they can't be copied.
Yeah. Yeah, because, you know, remember, it's like the space of like, in a sense, identical particles is strictly bigger than in the classical case, right? Like classically, you basically can have like, all right, you know, this spin in this direction, this spin in that direction, they're pointing the same direction. I permute them and no one can tell the difference. But remember, you know, quantum mechanically, you know, you can also have a permutation symmetric state up, down, plus down, up, which, you know, is a joint state of two particles. It's entangled. You know, arguably you could say, you know, the particles don't have states of their own. And, you know, it's not merely that, it's just like there's two particles that happen to be in the same state. So if you permute them, it's different. It's literally like the particles don't even have individual states. It's this entangled superposition. And, you know, if you permute the two tensor pieces, it comes back to itself in a way that, you know, can't be explained classically, you know, because classical mechanics doesn't have the tensor product, basically. Systems and quantum mechanics combine in a strictly different way than classical systems, which allows, you know, the space of permutation symmetric stuff or indistinguishable particles to be like much richer than it could ever possibly be classically. You know, like we've seen, like, you know, the state of two permutation symmetric particles, say it's like spin half particles, is, you know, it's non-trivial in the sense that like there's three basis states, say up, 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 down, plus down, up, and down, down. There's three of them. And, you know we can associate that with a spin one state. And we can use the Majorana trick to represent that as two stars on the sphere, a constellation of two stars. So in other words, we can think about, you know, this thing could manifest as like, okay, a particle here and a particle there. And when I, you know, swap them or whatever, it makes no difference. You know, they're two identical particles or like whatever. Like, for example, if you wanted to represent a spin one state on your quantum computer that only works with qubits, you could represent a spin one state with 2 qubits, as long as you had those 2 qubits, you know, constrained to be in the permutation symmetric subspace of their tensor product. So you can
this is what I was thinking of. I was thinking of quantum computation, and you cannot copy a quantum state. But I was wondering if you consider them bosons, if that could be done quantum computationally. But I guess not. I guess it's still a violation.
Yeah, yeah. I mean, yeah, and it gets at the sort of the semantics of these words we use. You know, what do we mean by copy? What do we mean by indistinguishable and so forth? Remember, in this case, you know, indistinguishability means indistinguishability with respect to the tensor product, with respect to the way that the quantum systems combine. And then we have this distinction with fermions and bosons that, you know, the oscillators that keep track of the number of particles in these states can, you know, actually, that reminds me, like, I was going to upload this little paper that I thought might be useful. One of these, no, not that one. That's the berry one. Sorry, my computer's like being very slow. There's a good image in this paper that I thought, okay, yeah, I like this. I thought this was a cool. Funny title. Back and Forth from Fock Space to Hilbert Space, a guide for commuters. So this, you know, goes into, you know, a lot of what we've talked about here.
This is Primo Levi? So this is from what, the 30s?
Where's it, Primo? Primo
His
Levi.
first name was Primo Levi.
Was a fucking.
So how could it be 2018? Oh, wait. Oh, I'm sorry. No. I guess they're referencing Primo Levi.
Primo.
Because he died about 70 years ago. Or more.
Like, you know, here's the difference between first quantization and second quantization. I hope this was like a nice way of putting it. Here in the first quantization picture, we have 4 particles, and the particles each have 1, 2, 3, 4, 5, 6 basis states. And so we say, oh, okay, you know, particle 1 is in state 2, particle 2 is in state 2, particle 3 is in state 3, and particle 4 is in state 6. So in first quantization, each particle has its own Hilbert space. We take the tensor product, and you know, they have some state in those Hilbert spaces. Maybe they're entangled, like whatever. We kind of flip the picture on its head with second quantization. Instead, we have a harmonic oscillator for each one of the basis states of the original particle Hilbert space. In other words, we take these horizontal lines and make them vertical. So we have 1, 2, 3, 4, 5, 6 oscillators, and we keep track of the number of particles in that basis state. So first quantization is you have like n particles, tensor product, and you specify, you know, like what's the state for each particle, and they can each, you know, basically have a separate state. Second quantization is like you count the number of particles in each of the original basis states of the first system. And, you know, that shift in perspective, you know, essentially forces you to treat the particles as quote unquote indistinguishable, whether permutation symmetric or antisymmetric. This is obviously an example of bosonic because we have 2 particles in one of these modes. Because after all, you know, all you care about is the fact that there are two particles in that mode. Which one's which? Irrelevant. They're indistinguishable particles.
Matt, can you post these papers?
Yeah.
On
definitely.
the
yeah, I'll put links to both of them on
the Berry and Robbins, and this one. This is Beji. Oh, whatever.
Yeah, a bunch of people. Any other questions, concerns?
Is everybody on vacation?
Yeah, well, I don't know. Okay.
So few people showed up.
Yeah. I was wondering where Victor was, where Andre was. Well, it's all recorded. As like a little finale, perhaps. I'm gonna show you something cool. So again, this is something which I'm like actively learning about, so I can't, you know, give you the full story here, but
is Primo Levi a university in Italy? Primo Levi was killed by the fascists about 80 years ago. But I see his name, unless it's a different Primo Levi. What is that?
The Primo Levi that I'm familiar with died by suicide. He survived the Nazis.
Oh, he died by suicide?
Yeah.
I
He
see his
survived the
name on this
Nazis
paper.
and he died by suicide.
I see his name on this paper, and then it says University of Texas at Austin. Maybe it's his great-great-grandson.
Well, it's a different Primo Levi.
Must be.
The only one that I'm familiar with is the one who wrote Ecce Homo.
He committed suicide, but during the Mussolini regime?
No,
Was he
later?
Later? But was he persecuted by Mussolini?
No, well, he was persecuted, you bet. He was in Auschwitz.
Yeah.
Why did he commit suicide?
He survived Auschwitz.
So why did he commit suicide?
You ever see that Woody Allen movie? It's like that. I feel like that movie came out around that same time. I think it was inspired by it. It's like a Woody Allen movie from the late 80s about a Holocaust survivor
Who commits suicide?
I forget what it's called.
Was that Zero Mostel who was in that movie?
No, not that one. This is a movie with had Alan Alda in it.
Oh, well. Moshe, why did Primo Levi commit suicide after surviving fascism?
Why does anybody,
Yeah,
But after going through all that to commit suicide?
Better question, yeah. Why does someone who didn't go through Auschwitz kill themselves?
what
Never know.
I will never forget is the very first sentence of his book, Ecce Homo. The book starts with the sentence, I was lucky. I arrived to Auschwitz in the spring of 1943. And I couldn't get to, how can someone be lucky getting to Auschwitz? He says, I was lucky, I got to Auschwitz. I remember I kept reading the sentence again and again.
But he survived. He survived Auschwitz.
He survived, yeah, he survived. And the reason he survived, the reason he was lucky is because when he arrived to Auschwitz, they had a shortage of workers.
Yeah.
So they increased the ratios. Initially, the food ratios were supposed to make sure that people are dead within 3 weeks. When he arrived to Auschwitz, the food rations were increased so that you would last for 6 weeks or something like this.
But he was not a physicist. He was a political person.
He was a pharmacist.
I'm sorry, he was what?
A pharmacist.
He was a pharmacist. Oh.
Pharmacist.
But he was a political activist. I mean, that's why.
I don't know how much he was a political activist. He was just a pharmacist, and he happened to be Jewish.
So how did he become famous? Why him and not somebody else?
Because of the book that he wrote.
Oh, because he wrote a book.
Read this book. Read this book, Ecce Homo.
I'm sorry. What's the name? I think
Ecce, I don't know how to pronounce Ecce or Ecce Homo.
Ecce Homo. Okay.
Yeah, and not the Nietzsche one. Let me just allude to this thing because it's cool. Before this as a kind of finale. The final piece in the spin statistics thing program by Barry Robbins and Atiyah is to, before we just chose a Y rotation. We were like, all right, let's just rotate the cross spins using a Y rotation. It works, we permuted. But ultimately the idea would be okay, you situate these particles in space or whatever. And then, the specific rotation that you do is going to depend on their locations in space. And so if you like switch their locations in space, you know, that's going to correspond like a certain rotation or whatever. And so the question is like how to, in general, find such transformations, especially considering the case where you have like n particles and you want to consider, you know, arbitrary permutations of those particles, not just like individual swaps. And so, you know, to make a long story short, this ultimately susses out to the problem of like, is there like a smooth map from the configuration space of like n particles treated indistinguishably in space to basically SUN, or like the group which will do permutations, you know, these like exchange rotations, but like generalized to permutations. In other words, we needed a map from like where the particles are to an operator that does the exchange rotation or the permutation rotation. And it's like, does such a map exist? And it's gotta like have these certain properties, namely that if you, you know, permute two of the particles or whatever, you pick up the -1. And so this problem, you know, was tackled, like it's sort of mentioned at the end of the Barry Robbins paper. And then it's famous, you know, British mathematician, Sir Michael Atiyah, you know, picked it up. And he ended up sort of making the thing kind of conditional on a certain unproven conjecture, which, you know, numerical evidence suggests is true, but no one's been able to prove yet. So, you know, interesting open problem. And I find it really fascinating because it involves a lot of the ideas that we've already talked about. So let's give like a very simple, very quick thing here. So here we have 3 particles arranged in 3D. And I can click on these guys and I can like drag them around. Now look, notice what's going on with these little white dots. They are tracking the relative locations of these particles to each other. In other words, if I have n particles arranged in 3D, then I can imagine taking one of the particles and like drawing the line that like goes out to the other particles and normalize that. So I just only care about the direction and get a constellation on the sphere consisting of like n-1 points. In other words, I have 3 particles. And so each one of these guys has a 2-star constellation that you know, corresponds to the, you know, relative directions. So you see, as I move this guy around, like these 2 guys are, you know, tracking each other or whatever, all right? So, you know, the point there is that if you have 3 particles in 3D space, then, you know, you can associate them with 3, you know, 2-star constellations. But hey, what do we know about 2-starred constellations? We can represent them as spin-1 states, which are 3-dimensional, okay? So using our trick, right, like we can, you know, take each of these points on each of the spheres, treat them as complex numbers, find the polynomial, use the Majorana formula, or however you want to fucking do it, you know? You could associate spinners with each of these 2 points here, and then take the permutation symmetric product, or whatever floats your boat. But, you know, let's just say we turn each of these states into a spin-1 state. So then we have 3 3-dimensional states. And the conjecture of Atiyah is that they will always be linearly independent, and so form a basis for all 2-starred constellations. And evidence seems to suggest that this is true. So, you know, if you would take, you know, the spin state or the polynomial, if you like, associated with this constellation. Again, I'm just thinking about these white dots, this constellation and this constellation, 3 two-starred constellations, each is associated with a 3-dimensional vector. So I get a 3, I could arrange those into the columns of a matrix and get a 3 by 3 matrix. And the conjecture is like that the determinant of that matrix is going to be non-zero, and that, you know, therefore these 3 vectors are going to be linearly independent and so form a basis. Now, the idea is that then what you can do is, okay, so that you get a linearly independent basis. Then you do the QR decomposition. Is that true? No. Yes. No? Just remind ourselves. Not the QR decomposition, the polar decomposition, sorry. The polar decomposition of a matrix into basically a unitary and a Hermitian matrix. And then only look at the unitary part. And then you're going to get a unitary matrix, specific, you know, a unitary matrix that acts on, that's 3 by 3. Okay. Now, in a sense, we've already, okay, so let me just repeat what I just said. 3 points, say, in 3D. You get 3 constellations, each of 2 stars, and so each can be associated with a 3D vector. Gathering up those into a matrix with those vectors as columns, we have a 3 by 3 matrix, which we then decompose into a unitary matrix and a Hermitian matrix, and then just look at the unitary matrix. That's essentially the transformation which we want. It takes us from the configuration space of where the particles are, and it gives us a matrix, which essentially is going to be an SU3 matrix. And it has the property that if I swap the locations of 2 of these particles in space, what it's going to do is lead to a permutation of the columns of that matrix. And that's going to give us our -1 that we so desperately desire. Classically speaking, if you could take this matrix that's basically an SU3 and tensor it with the 2 by 2 identity to get a 6-dimensional matrix. 6 dimensions is also the dimensions of if you just had 3 2-dimensional spinners. And it acts on those spinners by exchanging them. And so, you know, that's actually what you see here. So I take 3 spinners where the directions are associated with these arrows here. And, you know, these are their phases. And then given their like location in this space, I form this matrix whose columns correspond to the constellations, get the unitary matrix associated with it, multiply it by the 2 by 2 identity. And then that's 6-dimensional, and it acts on the space of like what happens if you take, you know, a spinner and then a spinner and then a spinner, and just they're just like concatenated together. That's 6-dimensional. And then, you know, you act with that transformation on these guys, and it has this property that we wanted. In other words, I'll show it to you in another form where there's only 2 of them, so it's a little easier to see. And so, you know, this formulation of it is essentially classical. If we then replace those spinners with our harmonic oscillator thing, you can think about it like, well, you know, if you had 3 spins, they each have 2 oscillators, well, that's 6-dimensional too, right? So then you can take your, you know, 6-dimensional matrix and have it act on, you know, the creation / annihilation operators, of which there are 6 in the in the oscillator formulation of spin. So what you're actually seeing here is the sort of classical version, where you're just sticking with the, you have n spinners, and you get this transformation from the configuration space of these particles, and you transform it. You can do the same thing in the quantum case, but where you're kind of upgrading that transformation to act on, say, for example, instead of the 6 dimensions of the 3 spinners, instead the 6 dimensions which are formed from the 6, say, annihilation operators of the 3 sets of 2 oscillators. Okay, so again, this is the classical version, but so you can see the original location here. What happens if we swap the location? You can see that the phase goes to the negative of itself. In other words, we go over here, and compared to where this guy originally was, the phase is pointing in the opposite direction. And then we come back around, and it comes back to itself. So there you go. Now, this map has like other properties, which may or may not be desirable. It seemed to me, as far as I can tell, the point was to show that such a map exists. So, I just bring this up because it's sort of fascinating. It's something I'm still trying to understand a little bit. Been reading these papers. But I bring it up particularly because, you can see that it's, using, it's yet another way in which the stuff that we've, talked about, over this summer, like rears its head again and again, in the initial Barry Robbins thing that I showed you guys earlier, where there's just 2 particles and we're treating the quantum case, it's like, the whole thing depends on this oscillator representation of spin. In this case, the idea of representing constellations with like polynomials, like, rears its head yet again. Here, the constellations don't refer to the spin states, but like actually to like the space of like physical directions in space, like the relative positions of these particles. And, we can form a map from like the possible locations of these n particles, into a map from those locations to, a linear transformation, which does like a permutation, basically, that has the property that if you swap 2 particles, they like get a negative sign. Using this, these tricks, like with the polynomials and the stereographic projection, it's like you get these constellations based on the relative locations of these particles. You treat them as like roots of a polynomial, stereographically project them, etc. Get those polynomials, arrange them into the columns of a matrix, play around with it. And, the permutations of the particles correspond to permutations of the rows of this matrix. And therefore you get the correct sign flip when you permute the particles. And so, this is sort of like yet another fascinating application of, the joys of, playing around with constellations as, sets of complex numbers. So anyway, I'm still working on some visualizations of this and stuff. You can see we're got our start here. So I'll write something up about all this and get it down on paper. But so I'll upload, that commuter's guide to Boxspace. I'll upload the Barry Robbins paper, and then I'll also upload, one of these papers by Atiyah, where he describes this construction in the context of the Barry Robbins problem, so you can get the full story there. Anyway, any thoughts questions, concerns?
Yes, yes. I just want to say once again, great. Really enjoyed it.
Thanks.
And really appreciate, Matt. Really appreciate. Keep doing it because I enjoy it.
Yeah, well, I tell you, I have these meetings and then, a day or two goes by and I'm like, I'm like, shit, there's so much more I have to tell you guys. So much
That's
more
right.
to share. And so, yeah, I just ended up spontaneously writing these. Like, I didn't even plan on talking about this, last week or whatever. And then I realized, got to talk about fermions. Got to talk about that spin statistics. And, I reread the Berry paper and I was like, heck, this is perfect. Got our oscillators, got the whole thing. Yeah, well, actually, I won't go into it here because, we're already going, talked about a lot of stuff. But yeah, I just wanted to mention, to Moshe that, and I'll talk about this more specifically, but like, another great application of the double oscillator construction of spin is in the theory of the quantum polyhedra. When we talked about quantum polyhedra before, it was like, you would take, say, 4 spin half particles, look at the overall spin 0 subspace. It's like 2-dimensional, and it's a quantum tetrahedron. And, by imposing that the 4 spins that you start with are spin half, means that the area of each of the faces of the tetrahedron is constrained to be a half. But you might wonder, like, is there a representation of polyhedra where you could have like whatever you want in terms of the area of the different faces? And essentially what you do is you use the oscillator representation of spin, so that instead of, say, for like a tetrahedron, instead of 4 spin half particles, you'd have 4 sets of 2 oscillators. And so then you can have like a variable J value, which in this case turns out to be like a variable area of each of the faces. And then similarly to here in the Berry-Robbins case, where we form these like exchange operators, which are like built out of like cross spins, so to speak. In the polyhedron case, like similarly, yeah, they build those same operators. And so you can look at them as kind of, moving spin quanta from, between the different faces of the polyhedron. And, then similarly, like as I was saying about the relationship between this sort of like enlarged Hilbert space and like the ability to like parallel transport or like keep track of what happens to spins when you parallel transport them, it turns out in loop quantum gravity, you can use these exchange operators to build up the holonomy operators that correspond to like loops in the space. So that like if you imagine going from like polyhedron to polyhedron, like through these different faces, you can build up the operator that's like sensitive to the curvature around that loop in terms of like basically these like exchange operators that act like across the spins of like 2 adjoining faces. So, indeed, to like understand that particular formulation of loop quantum gravity, you really got to be like handy with your spins. The whole thing is like a generalization of the theory of spins, in terms of like generalizing the idea of like a spin network to interpreting the vertices of the spin network as polyhedra or like intertwiners of spins, building the polyhedron operators out of the spin operators, and then ultimately using the oscillator construction for each of the spins to, quantize polyhedra, where the area can be whatever you like, and in terms of those, you can build the holonomy operators that are sensitive to the curvature after going around a closed loop in the resulting quantum spacetime. So, Yeah, indeed. Like all these tools are like essential to understanding that particular way of thinking about loop quantum gravity. So I thought I'd admit, because you were asked. At some point, I'll talk more about that stuff once I understand it even more. I have some code here that does. Well, yeah. Maybe we'll just look at that and then call it an evening. Wow, my computer's so slow. It's interesting. Oh, I bet this isn't going to work. Somewhat retarded reasons. Boop, boop, doo. Yeah, totally. Sorry. Ah, God. Sorry. My computer is behaving terribly. I don't know if it's Zoom or whatever, but everything's lagging. I
Are
may
you
not.
running Chrome?
It's just in general. I mean, like literally, like the mouse cursor was just like
Oh,
moving really slowly. Yeah, like
well, Chrome will do that too.
Sure, sure.
Yeah, you have to. That's a bad browser.
Yeah, I found. I've been using for a while there. For a couple of years, I abandoned Firefox because I thought Chrome was faster. But actually, new versions of Firefox are really quite snappy. I've been using that more often.
Yeah, there's a add-in to Chrome to make it less slow. It's basically, it saves the windows that are the tabs that are not that you don't care about. It does it automatically, and so it really speeds it up tremendously.
Yeah, that is definitely worth looking into.
Yeah. Otherwise, I like Chrome. It's kind of nice, but I don't like the fact that some add-ins were used to hack into Chrome.
Oh, really?
And so I'm a little scared about using it for anything secure.
That's fair.
Mm-hmm.
Poly. I think I put this down at the bottom of this, maybe. Oh, right. Okay. I'm gonna try this one more time, and if it doesn't work, then I'll do it next time. Whew. Whoa, where'd my cursor even go? That work? I don't know.
That add-in is called the Great Suspender.
Nice. I like the name.
Yeah.
Write that down. Oh, right. Yeah, the other thing besides my computer being slow is just, I rewrote this code and some dependency issues.
Well, guys, I have to leave, so see you again next week.
I have to leave also. I have a dinner to go to.
This guy isn't, oh, wait. Maybe he is working. Okay, stay for 5 more seconds.
Okay.
Okay.
1, 2.
Maybe it'll work. I don't know. Is it? Maybe not. Oh, look at that. Yeah. Look at that. It's a polyhedron.
Ooh.
Okay, whatever. Yeah, we'll talk more about it next time. But yeah, this is a quantum polyhedron, and it's built out of 4 spins, each split into 2 oscillators, 8 oscillators total, et cetera, et cetera, et cetera. We'll talk more about that next time. Thank you all for coming. Have a great week, and until next time.
Yes.
Thank you. Bye,
Thank
guys.
you, Matt.
See
Bye.
ya.